ASK Aviation School.
Hello and welcome to my channel once again. In the last couple of videos, I have started uploading videos on aircraft system, specifically on Airbus A320 family aircraft. My last video was on air conditioning system of Airbus A320 family aircraft. In that, if you would have noticed, I have not been there physically, and I have transitioned from me being there to those heavily animated videos. The primary motive or the aim to transition from me being there to that animated videos is for a better visual representation of those complicated diagrams. If you imagine, it would have been very difficult for me to draw all those diagrams. That's a primary reason. Okay, at the same time, I would like to hear from you all in the comments that how do you find the videos, how is the transition from me being there to those animated videos. And let's watch together the pressurization system of the Airbus A320 family today.
Welcome to the ASK Aviation School Training Program. Please note, system details may vary with aircraft MSN and configuration. This material is for general guidance and understanding only.
At 39,000 feet, the air outside your airplane window is, well, it's so incredibly thin and freezing cold that if the glass were to suddenly shatter, human survival would be measured in seconds.
Oh, absolutely. I mean, the atmospheric pressure up there is what, about a quarter of what it is at sea level?
Yeah, exactly. Without intervention, your blood just wouldn't absorb oxygen. Your time of useful consciousness before passing out it's actually less than 30 seconds.
Today, we are breaking down the A320 family pressurization system.
All right, so here's what we've got on tap. We'll kick things off with the fundamentals, why we even need this system. Then, we'll get into the nuts and bolts of the system's architecture and all its components. After that, we'll walk through how it works automatically, check out its safety nets and limits, cover what to do in manual mode and abnormals, and finish up with a quick knowledge check to make sure it all sticks.
Okay, first things first, let's really get to the heart of why the system is so critical on a modern airliner.
So picture this. We're climbing up to, say, 35,000 feet. The air outside is incredibly thin. I mean, there's just not enough oxygen up there for us to breathe. That's where the pressurization system comes in. It basically creates a safe, breathable bubble inside the aircraft, making sure everyone on board is safe and comfortable.
The way we do this is by controlling something called cabin altitude. Now, don't get this confused with the aircraft's actual altitude. Cabin altitude is really just the pressure inside the cabin, but we express it as an equivalent altitude. The whole goal is to keep that cabin altitude nice and comfortable, usually below 8,000 feet. Think of it like being in a mountainy town, even when we're cruising way, way higher.
To sustain the crew and passengers, the pressurization system maintains a safe cabin altitude, equivalent to a maximum of approximately 8,000 feet, specifically ranging between 7,300 and 8,000 feet during high-altitude cruise. The difference between that dense, pressurized internal air and the thin external atmosphere creates what we call differential pressure, or delta P. This pressure difference exerts massive force. The unlined airframe you see here is the physical container bearing that outward load. Managing cabin pressure is a complex structural engineering challenge. We must balance human physiological requirements against the sheer physical stress placed on the fuselage.
And you know what's really cool? The basic idea behind it is surprisingly simple. Just imagine the fuselage is like a big, sealed bucket. The air conditioning packs are constantly pumping air into this bucket. Then, the pressurization system's job is to precisely control how much air we let out of the bucket, and it does that using a part called the outflow valve. So, by controlling the air going out, we control the pressure inside. Simple as that.
The A320 relies on a dynamic, continuous flow of air. This airflow begins at the engines, or the APU, which extract hot, high-pressure bleed air directly from their compressor stages. That raw bleed air is sent to the air conditioning packs, where it is aggressively cooled and conditioned for human use. These two packs work together to pump a constant, unvarying mass of fresh air into the cabin and cockpit. With air constantly entering, we regulate the environment through a single exit, the outflow valve at the lower rear fuselage. Restricting this valve lets less air out, causing internal pressure to rise. Opening it wider drops the pressure. The precise mechanical modulation of this single outflow valve dictates the pressure for the entire system.
All right, so now that we've got the basic concept down, let's see how that simple idea translates into the actual system architecture. We'll take a look at the specific components that do all the work.
So the whole thing is fully automatic, which is fantastic. If you look at the schematic, you can see how it works. It's constantly getting information from other key aircraft systems, things like the ADARs and the FMGC. All that data flows into the controllers, and they use it to tell the outflow valve exactly what to do to keep the pressure just right. Okay, let's talk about the key players here.
The brains of this operation are two identical independent digital cabin pressure controllers, known as CPC-1 and CPC-2. This schematic details the architecture. The active CPC pulls landing elevation from the FMGC and pressure altitude from ADARs. Operating with active and standby redundancy, it transfers control automatically after landing or a failure. To ensure equal component wear, they automatically swap roles exactly 70 seconds after every landing. The CPCs direct the outflow valve's three independent electric motors. Motor 1 is paired with CPC-1, and Motor 2 is paired with CPC-2. The third motor is completely isolated from the automatic controllers, reserved strictly for manual operation by the flight crew. Because of this architecture, a failure of an active controller or its motor causes no disruption. The standby system takes over, requiring no intervention from the crew during normal flight. In the ground phase, before takeoff, the outflow valve is fully open. Driven by the ground function or the residual pressure control unit, this guarantees there is zero residual pressure inside the cabin while the doors are open. During the takeoff phase, pre-pressurization begins. As the throttles advance, the system pushes the cabin down at 400 feet per minute until it reaches positive 0.1 psi. This locks the cabin in tight and prevents a sudden pressure surge when the aircraft rotates. During climb and cruise, the system follows a fixed law matched to the aircraft's climb rate. It targets the highest possible comfort level, capping the maximum cabin altitude at approximately 8,000 feet, even if the aircraft is cruising at 39,000 feet. In the descent phase, the controller commands a descent rate, maxing out at 750 feet per minute, so that the internal cabin pressure meets the landing field pressure plus 0.1 psi right before touchdown. Upon touchdown, any remaining pressure releases at 500 feet per minute. Exactly 55 seconds after landing, the outflow valve fully opens. If the aircraft rotates but fails to climb, the abort mode triggers. The system stops the cabin from climbing and reverts the pressure back to the takeoff altitude plus 0.1 psi. By integrating directly with the flight plan, the pressurization logic insulates passengers from the rapid atmospheric changes of the external flight profile. If FMGS data becomes unavailable, the system degrades to semi-automatic operation. The flight crew manually sets the landing elevation on the overhead panel, but the active CPC still handles the outflow valve automatically.
But what if something goes wrong? What if the pressure difference gets too big, where the cabin altitude starts to climb too high? Well, don't worry. The system has a safety net, a set of built-in protections to handle just that.
We have two completely independent safety valves back on the rear pressure bulkhead. Their job is to protect the aircraft structure. If the pressure inside gets too high, more than 8.6 psi greater than the outside, they'll automatically open. And they'll also open if the pressure outside ever becomes 1 psi greater than the inside. It's a purely mechanical failsafe.
Now, what if the cabin altitude itself gets too high? Well, we get a very clear warning on the ECAM. If the cabin ever climbs past 9,550 feet, we'll get a master caution and a specific excess cab out warning. That's our cue to immediately start the procedure. Okay, so let's talk about the what-if scenario. What if both of our automatic controllers decide to take the day off? That's when we, the pilots, have to step in and use manual mode.
You'll know this has happened because you'll see a fault light on the mode cell push button. The ECAM procedure will tell you to select man mode. At that point, you're in direct control. You use this little spring-loaded toggle switch. Hold it up and the outflow valve opens, which makes the cabin altitude go up. Hold it down, the valve closes, and the cabin altitude goes down. You're flying the pressurization system by hand.
There is a 5-second latency in the ECAM display because of the backup pressure sensor's resolution. To target a specific vertical speed, the crew must apply very short inputs to the toggle switch and wait for the system to catch up. Selecting manual mode moves the responsibility for the airframe's pressure limits directly to the flight crew. The primary interface for monitoring all of this is the ECAM cab press page. Visual thresholds dictate the crew's response. The delta P dial turns amber if differential pressure drops to -0.4 or climbs above 8.5 psi. The vertical speed dial turns amber if the cabin climb or descent exceeds 2,000 feet per minute. The most critical indicator is cabin altitude. If the internal altitude exceeds 9,550 feet, the display turns red, indicating an active depressurization event. For extreme emergencies, the crew uses the guarded ditching push button. Pressurization sends a closed signal to the outflow valve, the emergency ram air inlet, avionics ventilation valves, and cargo valves, sealing the aircraft below the flotation line. This leads to a common check ride trap. If the pressurization system is currently operating in manual mode, the outflow valve will not close automatically when you press the ditching button. You must manually close it. Recognizing these thresholds and the manual logic of the ditching system provides the precise control needed to manage the aircraft's structural integrity during a failure.
It's absolutely critical to understand the difference between auto and man. In auto, the system is thinking for you. It's following a plan. In man, you are the system. You are directly controlling the outflow valve. And here is the most important takeaway for safety. After landing in auto mode, the outflow valve opens automatically to depressurize the plane. In man mode, it does not. It stays right where you left it. It is 100% the crew's responsibility to open it up.
All right, let's wrap this up by running through a couple of questions. This is the kind of stuff you'll definitely see in a technical interview or during a line check, so it's good to have it sharp.
First question, when does the system automatically switch from one CPC to the other?
The switchover happens automatically, 70 seconds after every landing. This is just to make sure both controllers get equal use over time. And of course, it'll also switch over immediately if the active one sails in flight. Okay, next one, and this is a big one for safety. When you're in man mode on the ground, what is the one thing you absolutely must verify before anyone opens the door? You have to check that the differential pressure, the delta P, is 0. You need to see that the pressure inside and outside the aircraft are equal. Let me say it again. The outflow valve does not open on its own in manual mode. It's on us, the flight crew, to manually open that valve and make sure the aircraft is fully depressurized before a single door is opened.
Question 1. What component actually controls the cabin altitude? The cabin pressure control system, primarily by operating the single outflow valve. Question 2. How many pressure controllers are installed? 2 identical, independent digital controllers. Question 3. What happens if the active automatic system fails? An automatic transfer to the standby controller occurs. Manual control is only required if both controllers fail. Question 4. What is the primary function of the outflow valve? It regulates the exit of conditioned air to maintain the target cabin altitude and safe differential pressure. That covers the A320 pressurization logic. Thank you for watching Ask Aviation School. Please like, share, and subscribe to support more professional aviation training. Mastering these controllers is a fundamental requirement for the safe command of any pressurized transport aircraft. Understanding the architecture is the first step toward managing the aircraft's structural limits in the flight deck. See you in the next lesson.
Once again, thank you, ladies and gentlemen, for supporting my channel. As my channel is growing, you all contribute a lot towards me. My request is to continue supporting me by subscribing, sharing, and liking my videos, and also for notification on time, I would request you to press the bell icon also. Thank you. Have a nice day.
ASK Aviation School.